This video is sponsored by Brilliant. This time our problem will have an interesting geometry construction, so bear with me. First, let's start with an equilateral triangle with the area of square root of 3. Then we will expand the left side of this triangle using the apex of this triangle. And we will use the line with the same length to expand the bottom side of this triangle from the bottom left corner, as you can see on the sketch. So those two blue lines are equal in length. And if we connect the ends of those two lines, we will get the line with the length of 2 square root of 13. So finally, we're going to connect the bottom right vertex of our equilateral triangle with the apex of our big triangle. And in this way, we will form another triangle. The question is, can we find the area of this constructed red triangle? So this awesome problem was sent to me by one of my subscribers who wanted to stay anonymous, and I'm going to respect his decision. But if you guys want to try this problem out for yourself, you can pause the video right now and then come back and check the solution. Alright, so let's solve this one together. First, let's do some labeling. Let's label all the vertices of our big triangle as ABC and the remaining vertices of our small equilateral triangle as D and E. And let's take a look at this equilateral triangle, ADE. We know that the area of any equilateral triangle is equal to the side squared times square root of 3 over 4. And we know that the area of our triangle is equal to the square root of 3. So we can write this equation. We can multiply everything by 4 to get rid of the fractions. Then we can simplify square root of 3 on both sides of the equation and get that s squared is equal to 4. This means that the side of our small equilateral triangle is equal to 2, and this is going to be an important information for us. Now, let's take a look at the line EC and the line AB. Remember, from our construction, those two lines are equal in length, so let's label their length as x for now. Alright, so from here, I have used the law of cosine to help me to solve this problem. Just as a quick reminder, the law of cosines applies to any triangle, and it states that the side squared of any triangle is equal to the sum of the squares of the other two sides minus the product of those two sides times the cosine of the angle in between those two sides. And as you can see, I have labeled the sketch on the right the same way as our triangle ABC on the left. And if we apply the law of cosines on the triangle on the left, you will get the following equation. Now, let's take a look at the sketch on the left. You can see that our triangle ADE is an equilateral triangle, so this means that all of its interior angles have the value of 60 degrees. And this is exactly the angle in between the sides AC and AB, so we can use our formula. Let's substitute all the values from our sketch. We will substitute the value of BC for 2 square root of 13. The AC will be x plus 2. The side AB will be x. And of course, the cosine in between AC and AB will be cosine of 60 degrees. Now let's expand by using the square of binomial, and since we know that the cosine of 60 is equal to 1 over 2, we can simplify the last term by cancelling 2, and after using a distribution expansion, we will get the following. Here we can cancel plus and minus x squared and simplify. And finally, we can rearrange those terms on the left side of the equation so that we will get this really awesome quadratic equation. Now there are really multiple ways to solve this quadratic equation. And you know what's interesting? That the problems like this quadratic equation are exactly why I enjoy practicing math in more interactive way. And that's actually why I've been using Brilliant. Their quadratic and exponential function courses fit perfectly with puzzles like this, where each step builds your own intuition, not just the final answer. What I really like is that you don't just watch someone solve things, you actually work through the logic yourself, step by step. Their courses are created by educators from MIT, Harvard, and Stanford, and they are designed for everyone, from age 10 to 110, whether you are starting out or already deep into problem solving. And the cool part is that everything is interactive. You're constantly solving, testing ideas, and getting immediate feedback, which honestly makes a big difference compared to just watching videos. They also have courses in coding, logic, and even AI, so it's not just math, it's full problem-solving platform. So, since Brilliant is sponsoring this video, you can get 30 days for free using the link in the description or the QR code on the screen. Plus, you will get 20% off an annual subscription. And how cool is that? Alright, so let's get back to our problem and see how can we solve this quadratic equation. So for this problem, I will again use my favorite quadratic formula. And just as a quick reminder, it states that if we have a quadratic equation of ax squared plus bx plus c that equals to 0, we can use the following quadratic formula. So you can see that in our case, a equals to 1, b equals to 2, and c equals to minus 48. So we can implement those values into our quadratic formula. Then we can simplify the terms under the square root, and we will get that this is equal to square root of 196, which is actually 14. Then we can simplify everything with 2 and get that x has the value of minus 1 plus minus 7. This means that we have two possible values for x, that x is equal to either minus 8 or 6. But the value of minus 8 actually has no sense, since the negative value cannot be the length of the line in a geometry. So we can discard this value and we will get that the only possible value for x is 6. Alright, so now let's clear our image and let's focus on finding the area of our red triangle DBC. So you can do this in multiple ways, but in this video I'm going to show you two different methods to find the area of this triangle, and those are the ones which I think are the most interesting. So the first method will include using the sine formula for the area of the triangle. Just as a quick reminder, we can obtain the area of the triangle as the 1/2 of the product of any two sides times the sine of the angle in between those two sides. And if you take a look at our big triangle ABC, you can see that we can actually apply this formula. The area of this triangle ABC can be written as 1/2 of the side AB, which equals to 6, times the side AC, which equals to 8, times the sine of the angle in between, which is the sine of 60 degrees. So we can simplify this, and we know that the sine of 60 degrees is equal to square root of 3 over 2, so we will get that the area of the triangle ABC is equal to 12 square root of 3. Now, let's take a look at this big triangle once again. And if you do this, you will notice that this triangle consists out of two triangles. The triangle ADC, this blue one, and our wanted red triangle DBC. So, let's try to find the area of the blue triangle ADC. And we can do this again by using the same formula. So the triangle ADC is equal to the 1/2 of the side AD, which equals to 2, times the side AC, which equals to 8, times the sine in between those two sides, which is again sine of 60 degrees. So we will again simplify this and get that the area of the triangle ADC is 4 square root of 3. Now it's pretty easy to find the area of our red triangle DBC, since its area is nothing but the difference between the areas of the triangle ABC and ADC. So we can substitute our values and get that our wanted red area equals to 8 square root of 3, and this is our solution. But what if you don't know this formula, or if you don't like it? Then let's use the method number 2, which is using 30, 60, 90 triangle. Again, as a quick reminder, the famous 30, 60, 90 triangle has all of its sides in the special relation 1 to square root of 3 to 2. So you're probably wondering, where is this triangle on the sketch on the left? Well, if you pull the height of the triangle ABC from the apex C and label the intersection point with the line AB as F, you can notice a new right-angled triangle AFC. And since this is the right-angled triangle with one acute angle of 60 degrees, this means that the other acute angle must be 30 degrees. And there you have it, our 30, 60, 90 triangle. So if we label the sketch on the right the same as the sketch on the left, for better understanding, we can clearly see that the line AC, which is hypotenuse of this triangle, has the length of 8. So this means that the line AF must be the half of it, so it has the length of 4. And therefore, the most important line for us, the line FC, will have the length of 4 square root of 3. And this is the line which we actually need, because this line represents none other than the height of our wanted red triangle DBC. But we need the base of this triangle as well, and the base DB is really easy to obtain, since it is equal to the difference between the line AB and the segment AD, so it must have the length of 4. Now it's pretty easy to find the area of our red triangle, as the base times height over 2, which equals the 16 square root of 3 over 2, and this means that the area of our red triangle again equals to 8 square root of 3, and again we have the same solution. Alright, so I really hope you guys enjoyed this super interesting problem. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this. Of course, if you found another way to solve this problem, like always, please guys, write it down in the comment section. I always enjoy seeing your different solutions to the same problem. And until next time, see you guys and take care.